Fragmentation is on everything you need to know about SQL Server indexes. Just a little bit about myself. I've been who am I? I've been a long-time DBA, over 30 years. I started out with Oracle version 3. Actually took on Sybase after that, which became SQL Server, which became where I am today. I'm actually, those are most of my strengths. I'm also taking on MySQL of late and actually delving into how it all works. But always been a DBA, working on the development side. I worked for SolarWinds for many years as their performance evangelist, and just recently moved to Quest as a sales engineer. So I'm excited to get back in front of the customers, working with their database problems. So it'll be kind of fun. But I'm always looking at performance, and indexes can actually help increase performance, especially when you're doing a lot of reading and you're trying to do a lot of getting that data back out of the database. So this is the agenda we're going to talk about today. We're going to talk about index structures, all SQL servers, all the different types. We're going to talk about row store versus column store. And then we're going to try to understand what clustered versus non-clustered is. We're going to talk about heap tables and how they're different from clustered index tables, as well as we'll look at covering indexes, filtering indexes. And we get to the column store, we'll actually look at memory optimized tables and what indexes work on those and why you'd want to use the different indexes. And then finally we'll talk about index maintenance and statistics. Okay, before we get started, I always like to level set. How many of you are developers? Great. How DBAs? Okay, about half and half. How about do about anything? That's my Twitter tag. yeah, that's the truth of it. In fact, I think it's getting more that way as all these technologies come in, being on-premise, on the cloud, all the different options we have now. How many are on 2017? How about anybody on 2012? So we got anybody? A few, okay. 2008? Just always like to see, okay. Some of the indexes that I'm talking about today won't work on those environments. Most of them are 2016 and above. So if you're in earlier versions, this might be a reason why you want to upgrade, especially if you're encountering performance. I know a lot of you can't if you're stuck on applications that aren't certified and such, but something to think about. Okay, so what is an index? Well, it can be an optional object associated with a table or view. It can be on one or more columns. It can be unique or non-unique. Unique keys help enforce data integrity. And then basically indexes can speed up data retrieval. They reduce I/O both in memory and physical on disk. SQL Server indexes can either be on disk or in memory type indexes. So you can have clustered versus non-clustered, filtered or covering. You can do row store, column store. You can do hash. You can do memory optimized non-clustered indexes. What I'm not going to talk about in this presentation are XML indexes, spatial indexes, and full text indexes. Let's face it, guys. Index classes can run 4 days. So me giving you 75 minutes of an index crash course is about all I can do. And I can't actually go into the more depths of the full text and spatial ones like I'd like to. Maybe that'll be another presentation down the road. But basically row store indexes are B-tree structures on disk. And what a B-tree structure is basically it has a root, it has an intermediate level, and then it has leaf levels. Now, if you can have 0 to n levels, if it's a 0 level index, it means it fits one page. Provides efficient navigation, just as like you look up in a telephone book, it's ordered. You can go to an appendix in any book and you can find where to go right away. Well, that's what an index does. So there are many different, there can be more than one level, intermediate level, or there may be no intermediate level. And then the leaf level actually contains a pointer to the data location. Now, if it's a heap, basically what it contains is a row ID. That row ID is an 8-byte row ID, which contains file ID, page ID, and slot number. If it's not a heap and it's a clustered index, Basically, the non-clustered index that are associated with that clustered index table is basically holding the cluster key at the leaf. So as you can see here, as I zoom into this root level, say I wanted to find row number 19. Well, I just go to root. Root will point to either the intermediate level, and if there is one, and then the intermediate level will point to the leaf level in this two-level diagram that I've got. And then you can see at the leaf level, there's going to be the row ID, like I said, if it's a heap, or it'll be the cluster key. If it's a clustered index, it'll actually contain the data, okay? Because really, a clustered index is just a sorted table by that index. Okay, clustered index then looks like this, where you have basically a root, an intermediate, and then the data really sits at the leaf. So in other words, I would never have to read more than, if I wanted to go get a seek, I'd only have to do 3 IOs, right? 3 logical IOs. Because I can go to the root, look up the intermediate, and there's my data right there. If I did a scan, though, I would have to do a full table scan, because it basically would have to read every row at the leaf level. So it's a little more efficient than a full table scan, but not by much. Okay. In a clustered index, the data is ordered by the clustered key. And you can only have one clustered key on a table because it can only physically be sorted in one way. It's natural that way. It's used to quickly retrieve data if the query contains all of the columns in that clustered key. It has to at least include the leading left column. If it doesn't, it can lead into a full table scan or a full clustered scan. And like I said, it's used by non-clustered index to look up table data. So best practices for clustered indexes, and typically most SQL Server installations, you have clustered indexes. That's the best practice way is to always put your tables in a clustered index. Preferably it has a unique key or primary key that rarely changes. And the reason why you don't want the cluster key to change is because that table data is sorted by that cluster key, so it has to move around. Well, if you're rapidly changing that cluster key, it's going to get really fragmented quite quickly, and it's going to really reduce performance. So you typically want to use something that isn't changing a whole lot. Primary keys are usually good. You also want a small or narrow fields in your cluster key. You don't want a big wide cluster key because think about it. Every non-clustered index you put out there on that same table is going to hold that cluster key. So if you put a varchar 5000, you've got very large non-clustered indexes in all of a sudden. So you want to keep it very small. And then you want to choose the columns that you're going to actually frequently sort the data by, because that data is sorted for you already, so it doesn't have to go through a sort. Examples here I've got listed of good cluster keys is an identity column or some composite key like a date and integer to just get a primary key. You can use a new sequential ID function. What it will do is generate a sequential ID, so it'll really pack the data and index pages completely. You won't have any wasted space. But also they are pretty large, and they're ugly looking. So I don't personally use it, but that's what Microsoft recommends you use. I would rather use an intelligent key that I'm going to be going after that data a lot. Now, a heap is basically a table that doesn't have a clustered index. The rows are not sorted in any order, and what SQL Server will do is maintain an internal unique key. You can't access that key, but that's how it keeps all the data together. The data is accessed with full table scans only unless you add non-clustered keys to the heap table. And then finally, you've got the non-clustered index, which is a separate object in the database. It holds only the index columns or the key. And if the table has a clustered index, like I said, the non-clustered index will keep that clustered key at the leaf level. Otherwise, if it's a heap at the leaf level, it's going to be a row ID. So typically, clustered indexes are much smaller. You only got a few columns, so they take up less memory footprint as well as I/O to actually read in more data. So here's just an example of all three of those objects. As you can see, my clustered table here, basically my non-clustered will just basically go to the row in the clustered index. In the heap, the non-clustered will point to the data, but remember that data is not sorted. So you might have to go many different places to get one logical row back, especially if it spans more than a page. Non-clustered row store indexes, basically what they do, SQL Server implicitly adds a cluster key to the non-clustered indexes. You don't have to specify the cluster key. A lot of people think they have to. SQL Server will do the right thing and add it for you, and if you've included it in your index creation for your non-clustered key, it won't add it again. But just beware that show plan and SP help index, they won't show you that it's containing that clustered key in the non-clustered index. You either have to use third-party tools or SP space use to see the actual size of that non-clustered index to see that. And here's just an example of a show plan here that I'm doing, or a help index. And you can see my two here that I've got covered, a covering index here, and then I've got my PK is actually on sales order detail of order ID and order detail ID. So you can see that basically I only see the columns that it's indexed for those two non-clustered, row GUID and unit price. I don't know that it's covering, and I don't know that it actually contains the cluster key by just using that utility. What you can do, and I kind of like this script, you can download it, it's from SQL Skills, Kimberly. She's got a SP SQL Skills help index, which really does print it all out for you. And so this is the result of just running that. And you can download it here with this link. But as you can see, my one covering index there, COV saw it up, basically did just contain unit price, but now I can see the columns in the tree, which is actually unit price, sales order ID, and sales order detail, and then also columns in the leaf as well. So you can see how big that whole tree is when I either navigate the tree to find the data and when I finally get to the leaf. That makes sense? Any questions so far? Okay. It's pretty simple stuff, but I wanted to get us all level set on one page. Here's how does it perform though. But so here's an example of a heap with a non-clustered primary key. I added a non-clustered primary key because otherwise it'd just be a full table scan. So you could just sit and see how much time that's spent to read the whole table. But basically, how I created this heap is I just selected, from sales order detail into, and I just called it a heap table. Then I turned around and I actually altered and added my non-clustered primary key. The results of this, basically, it brought back 192 rows. What I was doing was I was just selecting star from heap table, where a sales order ID equaled something. So I got 192 records returned, 128 milliseconds it ran. So pretty efficient with 195 physical reads. But notice in my execution plan, since it is a heap, I had to do a RID lookup. And notice the cost of that RID lookup, it's 99% of the whole plan. So it was really a lot of an inefficient way to do it. Now, I believe I helped myself by inserting into from a clustered index because the data was already sorted. And so I wish I hadn't have done that because I think it would have been a worse access plan or worse timing had I done that. You really don't want to use heaps in SQL Server, because of the full table scans. But so the only time I can think of that it would be really good to use a heap is on tiny tables or temp tables, where it's always in memory anyway, so you don't care. You never want to use a heap when you need the data sorted or if ranges of data are needed, if you're looking for a range. Clustered index example, here's that same query. This time I just, put my primary key clustered there to rearrange the data. So it's all ordered nicely, and I'm looking for the same sales ID. And you can see it's using my clustered key as well. And it basically did a seek, which is probably the best you can do when you're doing a clustered index. So it did an index seek, 192 rows again, 128 milliseconds, no change from the heap. That's why I think, I ordered that data in the heap, so it probably performed well the first time. As it gets misordered and fragmented and all that, it'd probably be bad. Notice my logical reads. They're down from 195 to 9, so a little bit of improvement, but I think my test I could have had a better test. Now, a non-clustered index example, and this is one I chose just because, well, did I skip one here? Yeah, I did. Excuse me, the clustered index example, this is an example of where you want to ensure you're using that left leading column. I've got order ID and sales order detail ID as my key. But when I run this query, hold on here, where I'm selecting where sales order detail ID equals something, and I leave out the order ID, basically it says, it turns it into a clustered index scan, which is a full table scan. Cost is 96% of the whole query, and even SQL Server sees that it's missing an index, and it's suggesting that I add this index on sales order detail, because it can't reference the middle of an index. It has to always have the left leading. So there's two ways to fix this. We could just, change the query and add sales order detail, or we could add that index. Now that would depend on how much hoops you have to jump in order to get it changed in production. Performance was really bad by doing that. 1.5 seconds or 1,500 milliseconds. CPU time was half a second. And look at my logical reads, 64,140. It actually did some physical reads too. So let's create the non-clustered index it says to do. So we create this, and I always set a statistics IO on and time on. And I actually clear the cache each run too, so I get valid things, valid timings. But basically, we're adding this non-clustered index on sales order detail. Now all of a sudden, it is using that. Let me get down there. But it actually has to go back and do a key lookup now because I'm using a non-clustered index that has to, holds the cluster key, so now it has to go back to the table and get the rest of the information. Timing is better though, 273 milliseconds instead of 1.5 seconds. Did 6 logical reads instead of 64,000. More physical reads though, because it had to go back and forth between the table and the index. Other types of indexes to consider is covering, filtering, and you can do a combination. But adding indexes isn't always the right thing to do. You've got to consider your insert, your update, and your delete activity. If you've got a lot of DML activity and that's important to you for the speed of getting the data in rather than reading the data, then you may want to go for, not put as many indexes on. The more indexes you add to your tables, the more maintenance. So it not only takes up storage, but it can hurt performance with the DML activity. Not only that, it can hurt read performance if you've got a non-selective index that the optimizer for some reason says, I'm going to use this index because it seems better, but it's not selective enough. That could actually slow down the query. Also, missing and stale statistics can slow down the query too and confuse the optimizer, especially if you start adding lots and lots of indexes. Now, covering index is one way to speed up performance that works kind of, it's kind of my favorite of mine in all the different database types I use. If you've got a lot of logical I/O and you want to reduce that I/O, what you can do is use the include clause and basically include all the columns from that table in the index. So it doesn't have to go back to the table. You avoid a key lookup when you do that. So if I create a non-covering index, and I can do this on order header, and I can say online order flag, and then include all the columns from order header's table, it only has to go to the index and reduces one read per row, at least. So it can be significantly faster. Other index types to consider is a filtered index. Filter index is when you need a small subset of the full table, and you can somehow filter it. Order flag, in AdventureWorks, if it's 1, that means it's online. If it's 0, it's ordered through some store or something. But the thing is, if you're always looking for 1, why not just filter the rest of the data out so it doesn't have to read through it all? So that's how you do a filtered index. And then combination is just a combination of a covering index with a filter on it. So here's an example where I've just combined the two and just looking where order flag equals 1. I'm going to walk through each one of these, so we'll talk about them more in depth. A covering index with an include, so I'm thinking, well, why don't we try that on my query? Now, if you remember, my query was select star. You would never do this in the real world. You should never select star anything in the real world. As developers, please don't. I know it's tempting because it's easier to include everything and not have to worry about adding new columns, but it just thrashes memory, uses up too much I/O. But remember, I select star, so in order for me to create a covering index for my query, I would have to include all the columns. So that's what I did. I dropped my covering index on order detail, and I recreated it and included every column in that table. You would never do this. This is not a real life example, guys. This is poor, sloppy coding. But in order to in doing that, basically, I'm now doing an index seek. And my elapsed time was 49 milliseconds. So it improved it. It reduced the navigation part of it. It almost made a clustered index again, if you think about it. Because when I do a covering index, basically what happens is all the include columns sit at the leaf level. It keeps the navigation part of the tree very narrow and very small, so it can read fastly, and then it's right at the data. So it's a clustered index in that way. So I really just did a poor man's way of creating a clustered index on that table. But it did improve performance. It did have more, less logical and physical I/Os too. Okay, let's see. It reduces I/O, I said that. It can also help improve deadlock problems. If you have deadlock problems, a covering index can help that because it keeps it in the leaf level. It doesn't really have to maintain it and lock the whole row if you do that. Okay, it can hurt performance if the covering index is too wide. This is why I'd never recommend doing this on a select star query. And also if you're doing a lot of bulk inserts, so that can slow it down if a covering index happens. And the question was, does the order matter in the include? I don't think it does. Because it's going to be at the leaf and get the data. Now, if it's one that's in your where clause that you want to be considered, then you'd want that in the navigation point. You wouldn't want that in the include. Okay, that was a nonsensical query. I shouldn't have ever used select star. So let's get a more real life example. And this is, it really has to do with the customer orders. And we're actually looking at sales order header, customer, person, sales order detail, and product to get customer ID, first name, last name, sales order, and we're actually looking for a specific product. I came up with this kind of problem where, just-in-time inventory for sales you might want to look at and see what your popular products are. So I'm looking here where their online order flag is always online, which equals 1. Last name like C, product name like Mountain, %42, color is black, and product ID is greater than 900. As you can see here, it's a sloppy query. Right away, and notice that what I've done is I've dropped my clean buffers, I'm freeing my cache, procedure cache, and then I run it. And right away we can see that I've got 2 high I/O steps. So order detail, 64,145 records are being returned, and order header is actually 19,513. It has to go through for logical reads. It actually took 2.2 seconds to run, and it took about a little over a half a second of CPU. When we go look at the plan, you can again see it's doing a clustered index scan. Now, and it does that in the sales order detail at 74%. And then it actually joins that with product and throws it into a hash match. And as you can see here, you can see it's actually the clue. I don't know if you guys ever noticed this, but the clue that the data here is a lot is the size of this bar. Very little data is returning from this step, more data from here. Okay, and it throws that into a hash match, and then it goes to order header, and it does an index seek, and it throws both of those results into nested loops. Now, SQL Server even says you should add a covering index. It tells me to add it on product ID and also include order ID and order quantity. So let's go add that. And when I do that, basically what happens is it's doing a seek now on my covering index on order detail. Cost is down to 1%. My cluster seek actually went up to 86%, and it seems like a costly step. Sorry. And you can see my order detail records, instead of 64,000 in some, it went down to 19 reads, logical reads. So instead of 2.2 seconds, it's down to 423 milliseconds. So much better just with that covering index. But I want to get rid of that high cost step on order header. So let's go see if we can do that. Let's add a covering index on sales order header. And this time, just put it on order header line. I guess it's not covering. Okay, so, and we can see that it did hardly anything by doing that. As we go up here, we can see it did come down a little bit in cost. Hardly any, same 19,386 as opposed to 19,513 with the covering index on sales order header. And basically the time was 300 milliseconds as opposed to 423. So not much difference here in timing. I got it to eke out a little more performance, but then you have to ask yourself, is it worth it to maintain that index for that little bit of performance? Or am I good to go with just one covering index? Because remember, every index you add, you have to maintain it. So as we look at my timings there of that little case study, you can see with the clustered index only, it was 2.2 seconds. With the covering index on detail was 423, and the covering index on header was 305. I don't think I'd add the covering index on header. I mean, I'd really have to need that performance in order to do that. So you kind of have to give those considerations when you're thinking about adding indexes. What about a filtered index? And like I said, it works well on selective data, small subset of a full table index. It can actually, filtered index give the optimizer more information than just plain statistics. The statistics you've got on a filtered index actually are more accurate than the full table statistics. So the optimizer will get smarter when you use filtered indexes. Filtered indexes also reduce maintenance costs because it only has to maintain the filtered index when the actual filter changes. So it's a smaller index too, less storage, so it can read more into memory much quicker. Ideal columns for filtered indexes are categories with small values, such as a bit, a flag, or any status. Columns with distinct ranges, like department warehouse, department ID or warehouse, any IDs that have distinct ranges of values. Or columns that have mostly null values. A good one is if you're always looking for open orders, or where it's, data is not null, you can put a filter on that, and then it won't have to look through all the nulls, so the unknowns, to find the knowns. You can't use filters when queries are using computed columns, and they have a lot of and/or expressions or using like expressions. They can't handle the complexity of all those. And they also have to worry about set commands when you're using filtered indexes. There's a whole list of set commands that it has to be. And so you've got to set these all to these values in order to create a filtered index. Problem is what if you have an application that actually happens to try to set them off? So here's an example of maybe an application running that says, it's hard-coded in the application to set ANSI nulls to off. When it goes to update, you're going to get this error. It failed to do it because the index was created with the set as being on. So you have to be kind of leery of using filter indexes if you've got a lot of different set commands and a lot of different applications going after it. So let's add a filtered index. And did I have that filtered index? Yeah, right here. I'm creating a non-clustered index on sales order, the online order flag, where online order flag equals 1. And it didn't use it. It instead used the clustered index seek. Reason why? Clustered index seek is probably the best way to go after any data. But also another reason why is my data there was data skew. Over 90% of the records were online. Actually 99, I think it's 1% were not online. So the optimizer saw that and said it's too expensive, I can't use that filtered index. So what if we use a filtered and a covering index, a combination of both of those? So again, I dropped that index, and I included, I created with online order flag, and I said include all my columns from order header that I'm accessing, and oh, by the way, filter it on online order flag. And it used it. As you can see here, it's using my filtered covering index. Cost is still 83%. I did get my logical reads down to, the order header is now just still 19,386. My time is no different at 328. So I really didn't do a whole lot in adding that index. So at this point, I should give up. I've tuned the query as much as I can. Okay. Other things you should consider with indexes is data compression, especially for row store tables indexes. They can actually save you a lot of space and speed it up just by compressing the data alone. Because if you think about it, compressed data, as it gets sent into the system, it has to uncompress it, so it takes more CPU resources, but it's less I/O, so it kind of is a great trade-off. There's two types of compression in SQL Server. There's page compression, which is an end-all be-all. It not only holds row compression, which is basically the simple compression of removing spaces, taking variable length columns and reducing all that size. But page compression actually adds to that prefix compression and data dictionary compression. So it's a little more complex, and it's recommended you don't use page compression unless you have update percentages of that data very low, and yet your scan rate is very, very high. So maybe in a data warehouse setting where you take things offline and do ETL, and then you're heavily reporting, maybe that's where page compression would work better. But like I said, data is stored in fewer pages, so it does increase I/O performance. It is not available only in 16, SQL Server 16 and above. And you have some trade-offs. Like I said, extra CPU resources are needed to compress and decompress. I've got a link here that will show you all the trade-offs. And there's a number of them that you should review if you're thinking of data compression. But I just took an example of this filtered covering index with compression equals row, and I did that whole combination index just to show you what that would look like. And to find this information out, this query, if you go to DMDB partition stats, join that with indexes and objects, you can get all of your index sizing. And the query is here that you can run. But basically, as you can see, my filtered and covering index here, if you can see that, is 4.8 meg. That's uncompressed. Now, you can actually run this stored procedure. It's called SP, estimate data compression savings, and it'll give you an idea of how much savings in size you can get. So if I'm running this, and I'm just running that function, passing the table name, and then I just say I want row compression, and it tells me my current size, and then it tells me the size with the that I'd get with the compression. And so you can see my fixed order one, which was 4, or which was one of these, which one? I think it was 4. Basically, now is 432K if I compress that. So I'll save by adding all that up about 130 megs just on that one table alone. So that's row store indexes. We talked about clustered versus non-clustered. We've talked about covering and filtered and a combination of such. Just remember they're all stored on disk. And you can compress them, but they get fragmented, and they are in a B-tree structure. Now let's change the tune to column store. Column store indexes are basically stored column-wise. And they aren't B-tree structures at all. And they can be clustered or non-clustered. A clustered column store index basically is the primary storage. So it's going to be the full table. Non-clustered column store indexes are good to use on row stored tables, especially if you have OLTP system, a highly transactional system, where all of a sudden your marketing or sales decided, oh, we need demographics, or we need to do these analytical queries and take down your transactional system. I've worked on several of those, and they're no fun to try to even out those workloads. But this might be a way to not have to create a data warehouse by adding just a column store index. Column store indexes are very good for analytical queries, where you're just going at a few columns and you're aggregating or summing, or you're doing all kinds of calculations on them, because it's very, very fast. And the design, and I just took that sales order detail table, I decided to create a column store index on order ID, order detail ID, product ID, and quantity. And how they're stored is in column segments. Each column segment is just a particular column that's compressed. And then each column segments are related to one another via a row group segment. So it keeps them in an actual row. So you don't lose the fact that they are related to other columns. Each row group segment can be 1,000,000 records, and then it adds another segment. So as you see here, I have 3 segments in storage, in the physical storage. Like I said, a column segment is where they're compressed, but the row group is compressed as well. And this compression will give you up to 10 times query performance. Not only that, column store indexes use batch mode or vector-based processing. What that means is with one CPU instruction, it can read all the columns. You know, it can do many more things in one CPU instruction than it could be if it was a row store index. And just doing that can improve performance 2 to 4 times. So why would you use column store indexes? Like I said, high level of data compression, up to 7 to 10 times, smaller memory footprint, great for queries that get a few columns, reduces physical I/O greatly. You can have large fact tables. If you have those, a column store index works wonderful on it. I've got an example of that. Or you can do real-time analytics on your transactional systems, which is great too. It avoids that data warehouse syndrome. Or maybe saves you some time. So let's create a column store index. And I'm creating this on ordered detail. And you don't really have the thought of covering. You just have to put the columns you want indexed in it. So I put order ID, sales detail ID, product ID, and order quantity. And then to actually get the sizes of this, I'm just looking at the DM partition again. And you can see the difference between my covering row store index and my column store index is almost 5 times the space savings. So there you go. It really compressed it, really did it nicely. Non-clustered column store index. Okay, so here we've got this one. Let's see how it performs. So I first did the covering index so we could get a time on it. And I changed the query somewhat. So we're actually going and getting total amount and total quantity for the customer. So I made it kind of analytical query. And so I just created a non-clustered index, and I used the covering index. And you can see that 38,620 reads. It took 355 milliseconds in elapsed time. And there it's using my covering index. Well, now let's go add the column store index. And to add a column store index, you got to use the keyword column store. So create non-clustered column store index. And I do it on the same column, sales order ID, order detail ID, product ID, and quantity ID. And it'll actually show you this cute little column store icon here and say, yep, it used the column store index. And let me see, where's my timings? Okay, here's my timings. It scanned 2, it read 1 segment, it did 0 logical reads, 0 physical reads. Isn't that magical? Didn't do anything, and yet it performed. Actually, it stores all of its information in lob data, so you have to look further to the right where you get lob logical reads, which it did 527, and lob physical reads, where it did 7. As you can see here, my time went down from 355 milliseconds in the covering to 263 milliseconds with the column store. Okay, non-clustered column store example, another example, is that basically I thought, well, if I could put, if I put a column store, non-clustered column store on header and do sales order ID, customer ID, and total ID. But I get this error because column stores can't hold computed columns. So total do happened to be a computed column. So I got this actual error that's saying can't do that in the column store. So it's just some caveats on column store indexes. Here's just another quick example. Here I'm just basically selecting order ID, order quantity, and joining that. And my covering index, the times was almost 3 seconds to run that. The non-clustered column store, 446 milliseconds. So almost 6 times better, or a little more than that. Clustered column store indexes. These are good for star schemas, if anybody's ever used a star schema. If you don't, and if you ever want to play with star schemas, there's a good data set out on the internet. This link points to it. It's a U.S. A Department of Transportation. It has years and years of every flight to every city of data that you can download and detail. And it's actually a star schema. And the tables that you download, there's an on time, and I did this for 2015, and you actually have the originating airport, the destination airport, and city, and the actual time it took, and the actual distance, all this good information. Then you have a bunch of lookup tables. You got city market, weekday, unique carriers, and then airport ID. So you can actually create a little star schema out there and play with it. So that's what I did, and I actually decided to create a clustered table. So I did an on-time cluster table. So as you can see here, I've got my primary, my PK is a primary clustered key. And then I basically just turned around and created a heap table out of that, just selecting it into. So, and then I actually took my heap table, and to me this is the easiest way to create a clustered column store, is basically first create a heap table, okay, and then basically create the column store index, which I did, on the heap table, and then you have to have a unique key on a column store index, so I added a unique non-clustered index for my unique key. So now I have a column store index, a clustered column store index example. So let's go see how this performs. And I wrote this little query that actually is attempting to find the most popular flights in the United States from where to where. And believe it or not, it was from Dallas to Los Angeles. I would have never guessed. But anyway, that's what this query is attempting to do. It's getting the originating airport and city and destination airport and city and the total elapsed time the planes were in the air. And then basically it joins all those tables and then does a group by and then actually does that sum. And as we can see here, I altered this and added the cluster key here. So this is just a reference to the cluster key. And you can see that it used it. I did a scan, and it actually took 8 seconds, or 8,000 milliseconds. Look at it, most of it was on CPU, 7,687 on CPU. Well, the only thing I changed in this query, instead of doing the cluster index, I changed it to my column store index, my clustered column store, and then referencing on-time heap here. And you can see it uses that column store index. And basically, again, it read some lobs, 607 of them, did 5 physical lob reads, but increased performance by 5 times. It went down to 1.4 seconds instead of that 8 seconds. And that's just by creating a column store versus a clustered index. Clustered index size and restrictions, you can look at the difference here. And so, when I look at my clustered index, it was 225 megs. When I look at, I had to include the my unique non-clustered index as well as my clustered column store index, but that was less than half the size, so much smaller. Only 17 meg went to the custom column store index, which held the data. So the other things you got to remember though with column store indexes, there are some limitations. It can't be on a view. They can use include, ascending, or descending. You can't alter the index. And there's other limits out there, so it's always useful to know all of those. Okay, so that's column store. The next index we have then is memory optimized tables, and you can have indexes on those. Now, memory optimized tables are basically just reside in memory. And you can create these memory indexes on top of them that aren't persisted, between reboots. It actually recreates these indexes on the fly as you start up the database. Non-clustered indexes are the best for ranges and order scans on a memory optimized table. And if you're in doubt, it's best to use this index, the non-clustered indexes. Column stores indexes, again, great for analytical queries. They can scan or aggregate over large amounts of data, so they're great to use. And then finally, you have hash indexes. Hash indexes can only be used on memory optimized tables, and they're only good for equality seeks. So they can't support ranges or ordered scans. In fact, the data doesn't come back sorted at all, and the data must include all columns in the index. So the query does. So you have to create the query. I mean, when you create the query, you got to make sure your index contains all the columns that it needs. So let's go see what an on-time table in memory looks like. So I've created this table. And the only difference between creating an in-memory table versus a on-disk table is basically you've got to put in the create table memory optimized equals on, and then you got to give it some durability. Schema and data I always use as a default. Now notice my primary key is non-clustered, and you first have to, if you're going to do in-memory tables, you have to first create a memory optimized file group. Otherwise, it'll give you an error. So you alter database, and you just add that file group, and you say memory optimized data. That's where it can store it. Then you alter data, and you give it a file for that file group. So here's our query that we're running again. And you can see it does use that query. And it did get it, just by putting it in on a memory optimized table, it did reduce it from that 8 seconds to 2.5 seconds. Not as good as our clustered column store index, but still, all I did was put it in memory as opposed to not putting it in memory. So that was an improvement. Now, a clustered column store index on a memory optimized table. How mixed up can we get with all this stuff, right? That's easy to do, though. We just recreate our in-memory table. But this time, I say, I want it, the index, clustered column store with memory optimized. That's the only difference with that. You can alter, in 2016, you can now alter clustered column store indexes. Before then you couldn't. You always had to recreate the table and included it with that. But there's our same query again. What did this do? Well, we're using that column store, that clustered index, and we got it down from 8 seconds to 888 milliseconds. So 9 times better performance just with that clustered column store index on a memory optimized table. So yes, we went there. Hash index, okay, we still got a hash index option. So let's try that. So again, we go back here, and remember hash indexes are only good on memory optimized tables, and they're only good when you're doing a single row lookup. So it's got to be a seek. So I changed my query somewhat, and I'm looking where the PK equals destination airport, and there's an ID in on time, which was the primary key. And really what I did is I first actually created this with a clustered index row store clustered index just to get a timing on it. Well, actually did a table scan in memory. And it got it down to 704 milliseconds. But let's add that hash to compare against. And with the hash index, you have to give it a bucket count. And I can't, I don't know what to recommend on that. I had what did I have? I think I had something like 2 million records in this table. And so I went with 150,000 buckets. I didn't know quite what that is, so I don't take my bucket count. But there is some reading that you can do to actually get that up there. Okay, so basically we run that query again, and you can see with this hash, and it actually says it's using my hash index, and it got it down to 42 milliseconds. So 16 times better in performance by using the hash index. So you got to consider what you're doing, but you know, the hash indexes on the memory optimized tables might be the way to go. Finally, I can't talk about indexes without talking about how to maintain them. They are another object in the database, or they are an object in the database that gets fragmented. You know, too many indexes on a table can slow down performance. You can actually, if you got a lot of DML going on, it can slow that down. And the optimizer may even stop using that index if it sees it's too fragmented. You can actually reference this one table, or it's actually a table value function called DMDB index physical stats to view the fragmentation. And basically, I just press the DB ID and then to get it for the whole database. And so you can see here for my product table, I had 50% fragmentation. I had, you know, for my product index, almost 8% fragmentation. My registration, which was a heap table, was 22% fragmented. So Microsoft recommends that if it's greater than 5% but less than 30%, you use reorganize. It's less impactful. You don't have to take it offline or do anything like that. If it's over 30%, you should use an index rebuild, but you can always rebuild online. Other things to think about is unused or little used indexes. Are they slowing you down? Are you taking up too much space? You need to usually find and delete those. This query here basically will help. And I've written this in my slides. If you download them, that you should just be able to cut and paste these and they should run for you. But you go to DMDB index usage stats. And as you can see here, I can see the number of seeks, the number of scans. I can see the index size. I can see the number of lookups, the number of dates. So it gives you a fair amount of information. Right here with my wage payment index, that's actually a primary key, it's never been used. I don't know why I'd want to get rid of a primary key, but it's probably maintaining data integrity, but nobody used it. So. And this is since last server startup, so you may have used it in some fashion, depending on how long you've had your SQL Server running. So it's not an end-all be-all, but it does give you some clues. And then finally, missing columns. Do you have you know, missing indexes out here? And you can run this DMDB missing index columns and pass it the index handle. And basically that'll give you all the missing columns that they think you should either include or add. What you really have to do first is actually find the index handle. And you do that through this table, get the handle, and then you pass it in this table value function. And it'll tell you, okay, you're missing a quality product ID, and you need to include sales order ID. Then finally, inserts, updates, deletes. Are they slowing down performance? You can look at operational stats. This is another useful index view that basically, again, it's a table value function, but basically you pass it the database ID, And the operational stats will come back and tell you how many singleton lookups, what's your range scan count, how many updates, how many inserts, how many deletes. So you can see how active this index is affecting you, or being maintained, if you will. And the last thing is sales, or stale index statistics. I really believe that the quality of your execution plans equal the quality of your statistics. So if you don't know how stale or how good your statistics are, might be the query that you can run to see that. And it basically just goes against sys indexes and sys tables, but it'll actually tell you your stats last updated, and it'll actually tells you the amount of rows that's changed since then, as well as the percent of rows changed. So for this top one, my new order table basically changed 98%, so maybe I should retake stats. I got done early, but I can take questions. But in summary, indexes can speed up your performance. They help, especially the slowest part of a computer is I/O, right? Especially disk I/O. But your memory footprint matters too. So you don't want to be thrashing that. So if you can reduce the data that goes in to actually get to the data that's needed, that's the greatest way to speed up performance in any relational database. It's important to know, too, which database index types you should use for different things. Row store indexes are good for online, transactional, very fast OLTP systems. Column stores are good for more data warehouse analytical queries. And just remember, memory optimized tables may help you if you really need that extra performance. And then look at your maintenance of your indexes. That might take you a long way right there. So that's it. Any questions? Sure. You have a lot of locking, or what? Okay. It just, when you're using parallel inserts?
Yeah, to update a column store table.
It just slowed everything down with the update. Yeah, the question was, he had a fact table that he did a lot of parallel inserts, and it was slowing, the parallel inserts weren't performing. And I could see that, because the column store has to, there's a fair amount of compression and everything else going on and getting it into that column store structure. That probably, CPU is probably quite high, especially if you're doing a lot of that parallel inserts throughout the day. If it's a heavily hit table with DML statements, you're going to have a problem with that. You might, well, what?
Restricted to a single instance to do the updates, or any other workaround?
You could try that instead of having all the processes out there working, because I imagine there's also a lot of latching or locking going on behind the scenes between the parallel processes, depending on how they're inserting. You could try making it, try to reduce hinting it with a degree of parallelism, not to go parallel. You could do a non-clustered column store instead. That might be better, because then you wouldn't.
So we want to take advantage of column store on the large table to do analysis.
I'm not understanding the question. I'm sorry.
The design is to take advantage of the column store on the large table, so I can do analytic queries. So if that's the design, then there seems to be ETL need to wait for the background compression to finish before the whole ETL process can finish?
Well, the compression on the column store index should be instantaneous when it creates it. And when you're inserting into it, it's going to do it all the time. So if you're continually inserting into it, it's going to have to continually create the new row groups and compress them as you're inserting. So I don't know how you can say, okay, stop the ETL process, because that the ETL process is actually causing that to happen. I mean, that's the whole idea of maintaining the index. So I guess at the end of the day, what you got to really ask yourself is which is more important, your performance on the insert or your performance in actually reading the data and getting it out. Because if it's reading the data and getting it out, the column store index is probably the best answer. But if you can't seem to get the data in, it's not going to, it's not helping you at all. So, and you might want to look at, you don't have to take the whole table. You don't have to make it a clustered column store. I mean, even if it is a fact table, you might look at doing a non-clustered column store on fewer columns for just what you need with the where clause, because that'll take off some of that pressure for inserting into then. And other things you can do, I mean, do you have it in memory? Is it optimized or is it too large for that? Okay, okay. Yeah. I mean, there's so many different ways you could try, but yeah, you'd have to test each one of those. Any other questions? Sure.
How many in-memory or optimized table can I have in a database?
How many?
Yeah.
It's how much memory you have to devote to that. And if you don't, like I had to actually cut down in mine. I had a little CPU VM, and no, I don't know how much memory, not very much memory at all. So I had to cut down the actual size of my on-time table to get it in memory, because it'll tell you, it'll say, don't have enough memory, don't have enough room. So, other questions? Well, thank you. Have a great conference.